Let us continue from our discussion in the previous lecture, and that is on the topic of synchronous counters. So in the previous lecture we looked at how we can design a synchronous counter quite easily for a counting sequence from 0 to 7. That is, it was a mod 8 counter or a 3-bit counter. So from that, let us now see how we can use that concept which we had developed for the synchronous counter to design a counter with maximum count of some number which is not the maximum possible count. So let us say we still want a 3-bit counter. We want a 3-bit synchronous counter, but it has to be a mod 6 counter. So mod 6 counter. That means the counting sequence must be 0, 1, 2, 3, 4 and 5. After 5, the count must necessarily become 0 and then again 1 and so on. So supposing we have to do this using T flip-flops, let's keep that fixed for the sake of discussion. So if we have to design a mod 6 counter, the maximum count is 5, so we will need a 3-bit counter. That is, we will need 3 flip-flops. That does not change. So suppose we now construct the state table which shows the present state and the next state. So if there are 3 flip-flops, let's say that we have Q2, Q1 and Q0 as the present state, and the next state is Q2 plus, Q1 plus and Q0 plus. So if the present state is 0, 0, 0, the next state has to be 0, 0, 1. If the present state is 0, 0, 1, the next state has to be 0, 1, 0. If the present state is 0, 1, 0, next state has to be 0, 1, 1. That is 3. If the present state is 0, 1, 1, the next state has to be 1, 0, 0. For 1, 0, 0, the next state has to be 1, 0, 1. For 1, 1, 0, however, for 1, 0, 1, however, the next state has to be 0, 0, 0. Because after 5, the count should go to 0. This is what the basic state table looks like. Now let us expand this in more detail to understand what will happen to the remaining states, that is 6 and 7, which are also possible in a 3-bit counter, but in this particular case we do not want to see them. So let us write them as present state, then next state. So Q2, Q1, Q0, then Q2 plus, Q1 plus, Q0 plus. Zero, 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 0, 0, 1. Oops. So when the present state is 1, 0, 1, the next state has to be 0, 0, 0. Now there are 2 more states remaining. That is 1, 1, 0 and 1, 1, 1. Now the question is, if the counter ever goes into these two states, what should we do? Well, logic tells us that they should come back to 0. Because when we were designing asynchronous counters, for the state 6, we forcibly tried to make it 0. So let us say we will do something very similar over here as well. So based on this, let us proceed in the similar manner and try to find what will be the t values needed for each of these. So T2 will be governed by Q2 and Q2 plus, T1 by Q1 and Q1 plus, T0 by Q0 and Q0 plus. That is, we are to see the excitation table of the T flip-flop. So I will not write the excitation table again. It is simply an XOR function of the present state and the next state. So 0, 0 means next. So the T2 required is 0. Again 0, 0, it is 0. Again 0, 0, it's 0. 0, 1, now it is 1. Then 1, 1 is again a 0. 1, 0 is a 1. 1, 0 is again a 1. 1, 0 is again a 1. Then for T1, Q1 and Q1 plus. 0, 0 means a 0. 0, 1 means a 1. 1, 1 means a 0. 1, 0 means a 1. 0, 0 means a 0. Then again we have 0, 0 which is a 0. 1, 0 which is a 1. 1, 0 again a 1. Then Q0 and Q0 plus. 1, 1, 1, 1, 1, 1, 0 and 1. That's it. So now we have T2, T1 and T0 as functions of Q2, Q1 and Q0. Once again, let me emphasize that you cannot express these as functions of the next state, because technically these two are the same variable. So you cannot say it will depend on the present state and the next state. Well, technically, if you look at it very closely, the value of t that is required, we are finding out by looking at the present and the next state, but all said and done, we only have access to q. We don't have access to q plus. So therefore, let me write T2 as functions of Q2, Q1 and Q0. Let's say some F1 of Q2, Q1 and Q0. If I write it in the sub form, the min terms are 3, 5, 6 and 7. T1 is some F2 of Q2, Q1 and Q0, and that is the midterms which involve 1, 3, 6 and 7. T0 is some F3 of Q2, Q1 and Q0, and that is the midterms are everything except 6. So that is 0, 1, 2, 3, 4, 5 and 7. So using this, we can solve for T2, T1 and T0. So let's do that. For T2, the K map would look like this. So the midterms are 3, 5, 6 and 7. 3, 5, 6 and 7. So here it looks just like the carry of the full adder. So we get T2 is equal to Q2, Q1 plus Q1 Q0 plus Q0 Q2. For T1, the K map looks like this. So the midterms for T1 we derived are 1, 3, 6 and 7. So one group this way, the other group this way. So we can say T1 equals Q2 Q1 plus Q2 bar Q0. This is T1. And for T0, the K map would look like this. So except 6, all are 1s. This is what we can do. So we can make one group of 4. We can make another group of 4 and another group of 4 in this way. So T0 in this case would be Q2 bar plus Q0 plus Q1 bar. That's it. So we can now draw the logic diagram, which would be little complex. Suppose we have these 3 flip-flops. So we see that T2 is a big function of Q2, Q1 and Q0. So essentially it would look something like this. If I were to use basic gates, it would be kind of like this. One OR gate and 3 AND gates. T1 would be Q2 Q1 plus Q2 bar Q0. So again, if I have an OR gate, we would now need 2 AND gates. The inputs would be Q2 Q1. You could even reuse this gate, there's no harm in that. Then Q2 bar and Q0. And T0 would be Q2 bar plus Q0 plus Q1 bar. So again we will need 1 OR gate and 3 inputs, Q2 bar, Q1 bar and Q0. What is most important is that we need to show the clock input. The clock will be the same for all the flip-flops. And we must mark that this is the MSB, Q1 is the second bit and Q0 is the LSB output. This is the counter. Now what we notice is that the circuit now is becoming a little cumbersome. Apart from these flip-flops, we are needing 1, 2, 3, 4, 5, 6, 7, 8, almost 7 or 8 extra gates, which is making this circuit a lot more challenging than it actually is. when it is in the asynchronous form. So if you remember, when we were trying to design a similar circuit, that is a mod 6 counter, which would count from 0 to 5, but using the asynchronous technique. The only difference was that the circuit was asynchronous and we were using a logic to activate the clear inputs for every flip-flop, and for that we just needed one additional gate. So therefore what we are seeing over here is that this is just one more case where the statement which we made towards the end of the previous lecture, that still holds. Now what was that statement? We had said that while synchronous counters are faster, they demand more logic circuits. They demand a lot more additional gates usually when you compare with an asynchronous counter for the same application. You can see the asynchronous counter, to achieve mod 6, it made use of only one additional gate. But here you need about 7 or 8 additional gates, and that is a lot. So the question is, can something be done to reduce these extra additional gates? Well, let's see. When we were designing this synchronous mod 6 counter, we had proceeded in such a way that the state diagram looks like this. After 0, we would go to 1, then to 2, then to 3, then to 4, then to 5. Then, after 5, we come back to 0. And since the count is a 3-bit value, it could even take 6 and 7. But what was happening was that we forcibly made the 6 and 7 to converge to the next state of 0. Now, when we look at this state diagram, we see that this is the main counting chain that we are concerned about. 6 and 7 is not all that important, because something tells us that, well, if the counter starts counting, as long as this counting chain is maintained, 6 and 7 will not normally come across in the sequence. So therefore, rather than forcing these to come to 0, why not we leave them just the way they are? If the present state is 6 or 7, then we will assign the next state as don't care. Let's see how that works out for us. So suppose I say, now my truth table would look like this, the state table. So what I will do, assign 6, 7 to don't cares, and so here next state will be 1, then 2, then 3, then 4, then 5. Now for 5, the next state would be 0. Now when the present states are 6 and 7, let us assign the next states as don't cares. Okay, so now what would be T2? Let's write it by looking at these two columns. So here until number 5, it would not change. Then we have T1, which we can again fill. This way, and T0 is this. So the K-map for T2 can be now constructed like this. So 3 and 5 have a 1, 6 and 7 have don't cares. So what I can do, I can just make two groups like this. So T2 would be equal to Q2 Q0 plus Q1 Q0. This is what T2 would be. Now for T1, the K-map would look like this. So over there, for T1, we see that the ones are at 1 and 3, and 6 and 7 are don't cares. So we can simply make a group like this, and T1 would be Q2 bar Q0, and for T0, you don't even need to construct a K-map. You can simply say that you have 6 ones and 2 don't cares, which make it T0 will be equal to 1, because all the 8 can be grouped together. So now what would our final circuit look like? Let us draw that. So we see that T0 is now 1. T1 is Q2 bar Q0. So all we need is one AND gate. This is it. And T2 is Q2 Q0 plus Q1 Q0. So we will need one OR gate and two AND gates. So Q2 Q0 and Q1 Q0. Of course, the clock must be shown. Where again Q2 is the MSB, Q1 is the second bit, and Q0 is the LSB of the count. But now what we see is that the number of additional gates required is just 4. Compare this with the earlier case where we were forcing 6 and 7 to go to 0. We needed 8 gates, 7 or 8 gates. So therefore, with this technique, in this technique, what we are doing, we are taking the states 6 and 7, and the next state, what we are assigning them is don't cares. So therefore, with this, we have reduced what our circuit additional requirement is. But having said all this, all said and done, what we are seeing is that we should not pat ourselves on the back and say that, okay, we have now reduced the hardware, we have reduced the additional complexity or additional gates needed, and now our problem is solved. No. We have assigned 6 and 7s to don't cares. So now we have to ask ourselves, if by chance this circuit enters either 6 or 7 state, how will the circuit react when the next clock comes? Will they change their state or will they still remain in the old state? That is very, very important. Now you may question, but will 6 and 7 come? Will we encounter 6 and 7 while the circuit is counting? Well, as per our state table, no. When the circuit is counting from 0 to 5, you will not encounter 6 or 7. But suppose there is some noise, or when you are switching the circuit on, when there is no clock, the flip-flops might have some default state value, and that can be anything. So therefore, let us see through the equations that we have derived. Let us see what will happen if the present state is 6 and the present state is 7. So before doing that, we'll have to draw what the current state diagram is. This is something we have ensured so far. So when we get 6 and 7, right now we do not know what that will be. So therefore, let us write what is T2, T1 and T0. So what we derived the expressions was that T2 is Q2 Q0 plus Q1 Q0. T1 is Q2 bar Q0. I guess that is correct. Yes. And T0 is 1. Okay. Now suppose, let's take case 1. If the present count Q2, Q1, Q0 becomes 6, that is 1, 1, 0. If Q2, Q1, Q0 is 1, 1, 0, that means Q2 is 1, Q1 is 1, Q0 is 0. Then what will be the values of T2, T1 and T0? So then in this case, T2 would be Q2, Q0 plus Q1, Q0. So Q2 and Q0 would be 0, Q1 and Q0 would be 0. So T2 would also be 0. And what about T1? T1 is Q2 bar Q0. T1 is Q2 bar Q0, which is also 0. And T0 is always 1. Now we know what is the value of T, each of the T's, and we know the present state. So from this we can calculate the next state, that is Q2 plus, Q1 plus and Q0 plus. Now when T2 is 0, when T2 is 0, Q2 is 1. So therefore Q2 plus will continue to be the same state as Q2. Likewise, Q1 plus will be the same as Q1, that is 1. However, here T0 is equal to 1. So Q0 plus will be equal to Q0 bar, that is 1. So if the present state is 6, the next state is 7. So now things get interesting. This 7 now becomes very crucial. So if the count is all ones, then what about the t's? So T2 will be Q2 Q0 plus Q1 Q0, which will be 1. T1 will be Q2 bar Q0, which is 0. And T0 is always 1, that does not change. So now let us try to predict what will be Q2 plus, Q1 plus and Q0 plus. So Q2 plus will be, T2 is 1, so it will be the opposite of Q2, which is 0. T1 is 0, so Q1 plus will continue to be Q1, that is 1. And T0 is equal to 1, so Q0 plus will be Q0 bar, which is 0. So this means the next state is actually 2. So what we are saying, if the present state is 6, the next state is 7, and if the present state is 7, the next state is 2. So therefore, we can now redraw the state diagram as so if the present state is 6, the next state is 7, and the next state is 2. So what we are seeing is that even if these are the undesired states, these are coming back at some point to a part of the known chain. These are coming back to the known chain. So what have we seen? We have seen that so far you can design a synchronous counter where there are some undesired states. You can forcibly make them 0, or you can assign those as don't cares. But if you are assigning don't cares, make sure you know which will be the next state if those undesired states are ever encountered. It may so happen that the undesired states may keep oscillating between themselves and they may never come as part of the main chain. In that case, it is disastrous. So, while the method of using don't cares for the next state in case of the undesired states helps us in reducing the additional logic complexity that is needed, there is a danger where we initially do not know what will be the next state of operation if any undesired state comes. On the other hand, if we are forcing them to a known state like 0, then we are ensuring that in spite of additional increased number of logic gates, we are able to ensure that those undesired states definitely converge into a part of the known counting chain. So this is how you can work with synchronous counters. Now, synchronous counters in general can be used to generate random counting sequences. So we will call them as sequence generators. We will call them as sequence generators. Now let us say you want a counter which will count only the odd numbers or only the even numbers. So let us say odd up counter. Odd up counter. So let us say the counting sequence would be like this. I have a 3-bit odd counter. This is what we want. This is what we want. So we can again follow the same approach using the state table, but this time let us use some other kind of flip-flop. Let us use the JK flip-flop. So let's say I have the present state. So I will say Q2, Q1 and Q0. Next state is Q2 plus, Q1 plus and Q0 plus. So if the present state is 0, let's keep the next state as don't care because it's not a part of the counting chain. When it is 0, 0, 1, the next state has to be 0, 1, 1, that is 3. When the present state is 0, 1, 0, again we will keep this as don't cares. 0, 1, 1, it must be 5. 1, 0, 0 will be don't cares. 1, 0, 1 will go to 1, 1, 1 because after 5 we should get 7. 1, 1, 0 is again don't cares. 1, 1, 1 must come back to 0, 0, 1. So now we will need 3 JK flip-flops. So therefore we need to fill values for J2, K2, J1, K1 and J0, K0. So this will be little bit more longer table, but we have to fill in these as per the excitation table. So if you recall, for the JK flip-flop, the excitation table looks kind of like this. 0 don't care, 1 don't care 1 and don't care 0. So let's look at Q2 and Q2 plus. 0 don't care means it could be either of the first two states, so therefore it is don't care, don't care. 0, 0 is 0 don't care. 0 don't care again is don't care, 0, 1 is 1 don't care. 1 don't care could be any of these, so again it is don't care, 1, 1 is don't care 0. 1 don't care is don't care, 1, 0 is don't care 1. Likewise J1, K1, we need to look at Q1 and Q1 plus. 0 don't care is don't care, 0, 1 is 1 don't care. This is like this. We will fill up all the rows. So now Q0 and Q0 plus for J0 and K0. So over here, some things you can make out manually. For K0, we just see zeros. Others are don't care. So you can very easily say K0 is 0. That's it. You can consider this don't care as 0 and make a group of 8. Now J0 is very interesting. You can make J0 as either 0 or 1. It seems it does not matter. So therefore, let J0 be equal to 0. Let's keep it same as K0. In both these cases, you can see J1 and K1 are both 1. So J1 equals K1 equals 1. For J2 and K2, you will need to construct the K-maps. So let's construct that. Let's construct that. For J2, the K-map would look like this. So we have don't care 0, don't care 1, and the rest are all don't cares. So this is Q2, Q1, Q0. So one thing you can do is you can make a group of 4 this way. So we see that J2 is equal to Q1. For K2, the K map would look like this. This should be 4, 5, 6, and 7. But anyway, it doesn't matter over here. So for K2, you have don't care, don't care, don't care, don't care. Then 1 don't care over here, a 0 over here, don't care, and a 1. So we can again make a group of 1s like this. So what we see, K2 is also equal to Q1. So the circuit now would look something like this. So let's say J0, K0, Q0 and Q0 bar, J1, K1, Q1, Q1 bar, J2, K2, Q2 and Q2 bar. So we saw that J2 and K2, we can make both as 0. J1 and K1 are both 1. J2 is equal to Q1, K2 is also equal to Q1. And we need to show the clocks as well. Where again Q2 is the MSB, Q0 is the LSB. Now I leave it to you as an exercise to find out what will happen for the undesired states, that is 0, 2, 4 and 6. What will be the next state? Will this circuit work? Well, that you have to see. So in this particular lecture, we saw how to design synchronous counters or synchronous circuits for different kinds of counting. We saw that we can generate any count using any flip-flop in the synchronous technique. In particular, we saw a mod 6 counter and we saw a 3-bit up counter for odd numbers. But using this technique, you can generate any random count also. Suppose if I have to generate 2, 1, 6, 5, 4, then 7, I can still do that. all I have to do is design my state table properly. And we also saw two techniques. One, where the undesired states are being forced to 0 or some known state as a next state, which is very, very demanding in terms of additional logic needed. And the second technique is where the undesired states were left as don't cares for the next state, which reduced our additional gate requirement considerably. But the danger over there is that you will need to ensure that those unwanted states come back to the desired counting chain at some point or the other. Thank you.